Hi everyone, this is Emrah Turgut. We will continue chapter 27. This is lecture 3, and we have thin film interference and polarization concepts. So when you look at let's say a soap on a water or oil on a water, you see different colors. It varies by angle when you look at it. So the fact is that the soap layer or the oil layer are very thin and close to the wavelength of the light in the order of micron. So we can see the interference effect from the thin film, and then we can see certain colors. That's the physics behind that. So for example, this is showing a one like physical picture. The light comes, reflects from the top surface and also reflects from the bottom surface, and the two light reach our eye, and they have some path difference like two slit experiment, and depend when they have a constructive interference we see the color. If it's a destructive interference we don't see the color. So there are a lot of applications for some filters on the cameras or lenses, also some let's say camouflage of some flights, the airplanes, jets. So this technology has been used a lot. So it's the same thing with a little bit simpler picture. So you have two light, one is coming from the first surface, oil and in air, and the second one comes from the oil and water interface. So we can calculate the path difference to be able to see what kind of colors we can see. You don't have to have a straight like a film. Also you can see this effect by making a wedge. If you have two microscope glasses, so you can let the touch to one side, and you can put some thin let's say hair on the other side, then you can see the varying the diffraction, like interference patterns along the glass. So as you go different locations on the glass, you will see that the path difference is gonna change. For example, and when we are close to the contact point A, it's a very short distance, but as you go further it's a longer distance. So what kind of problems we can get and how we can approach to solve them. First, interference occurs when two or more waves arrive simultaneously at the same point in the space. Constructive interference occurs when the waves are in phase. For example, phase difference can be 0, 2 pi, 4 pi, 6 pi, and etc. Destructive interference occurs when the waves are out of phase, which means that the phase difference must be pi, 3 pi over 2, 5 pi over 2, and so on. Oh, sorry, it's not about lambda. Either pi, 3 pi, 5 pi, 7 pi, and so on. So for example, I got confused. For the constructive, either it's a 0, lambda, 2 lambda, 3 lambda, and so on. For the destructive, it's a lambda over 2, 3 lambda over 2, and so on. So but in terms of angle of between two waves, what you need to know is these. So these lambda and other ones can be confusing, so I will delete them. It depends on the medium. So, but this fact, pi 0, pi 0, 2 pi, 4 pi, 6 pi is for the constructive interference, and pi 3 pi 5 pi is the destructive interference. Okay, one confusing part in this subject is this extra half wavelength shift occurs when the light reflects from a medium with a higher refractive index. So how it happens is, let's see, for example, let's think about it, this wedge. So first the light comes from this interface, and you see the light reflects from this interface, the glass and air. So the air has this called the NA, and this is NB, I guess. NA is the glass is larger, so there's no phase shift because of from the reflection. However, at this interface, the NB, the glass, I think it's the first one and the second one. So this is a little bit confusing, but you can ignore this. You can call this the glass is larger than an air, so the half cycle phase shift occurs. So you can think in terms of a rope wave. So this is how always keep in my mind. Let's say you have a wave. It goes this way. From the reflection, it will have a phase shift. So this is gonna be the reflected wave, and so this means there is a phi phase shift at the interface. So this is say soft medium or hard medium, the wall. If you have a opposite way, or you have a condition, let's say soft and hard medium, let's say the wave comes same fashion, say, and the reflected wave is gonna be in the face. So this will be the reflected wave. So this thing happens in the light as well, for electromagnetic waves. When the wave hits at a harder surface, it has a pi phase shift. So in this case, the path difference is taken through this wedge. So it's about this 2t, if you assume that thickness t at that point. So path difference is 2t. So and okay, let's ask about the bright fringes condition. So bright fringe means the phase difference must be 0 or 2 pi or 4 pi and etc. So, or it means that it's gonna be 0 lambda, 2 lambda, and so on. So if there is no any phase difference, 2t being equal to m lambda will give the bright condition, but you already have a phase difference. So let's say this is your first wave and the second wave. For the first wave, the phase difference, let's say it's gonna be 0, right? I assume this is our reference. For the second wave, path difference is going to be 2 plus 2t plus lambda over 2 because of that phase shift at this point. So to be able to have constructive interference, they must have 0 or lambda or 2 lambda path differences. So let's say 2t plus lambda over 2 must be either lambda, 2 lambda, 3 lambda, and so on. So if you give that m, just some number for that coefficient, then 2t must be m plus half lambda. So if you put this lambda in the right hand side, lambda over 2, you can subtract. I mean, having the subtraction and addition doesn't matter at this point. So it will be same, just because m goes from 1, 2, 3, 4, 5. It's always like 2t must be either lambda over 2 for m equals 0, or 3 lambda over 2 for m equals 1, and so on. So that's one counterintuitive phenomena in the interference of the thin films. Okay, so we have one problem here. So two very flat plates of glass are touching from the one side but separated from the another side. When the plates of glass are viewed by the reflection from a sodium lamp, let's say you have a light source and you see the interferences, evenly spaced, dark bands, and seen. If the nylon filament is now replaced by one that's slightly thicker, so this is the first case. In the second one, I am just exaggerating, you increase the thickness of the nylon. So what's gonna happen? The dark bands spread farther, dark bands move closer together, or doesn't change. So for example, how can we approach this problem? So let's say you have one dark region here, and if you go further by after lambda path difference, you have another dark point. This is, let's say, in the middle. You have a bright here. So bright and dark, bright and dark. So the path difference comes from the distance between, if you compare just the adjacent one, this extra height gives that path difference, and it allows to have a change from bright to dark, bright to dark. When you increase this angle, now angle is larger. What's gonna happen here is that, let's say you have a dark, and you don't need to go too far to have this the height change, because the angle is right now larger, and if you need less less distance, let's say less distance to have the same height change. So let's say for this you move, let's say 1 centimeter for lambda change. In this case you move, let's say 0.5 centimeter for lambda change. So then what you're gonna see, the bright points are gonna be closer and darks are gonna get closer. So the dark bands are gonna move closer to each other. Okay, we have one problem. I didn't put the picture here. Sorry, but in the question, you have a wedge of glass. You have a touching point at A, and B side has some thickness. So it asks, is the point where the glasses touch the point A? Do you have a dark fringe or bright fringe? So if you look at the, like it asks about this when you look at from here. When you look at from this side with your eye, what you're gonna see, is it dark or bright? So one thing, like we did when we talk about the first wave and second wave. In the first wave, let's say you have a reference 0. For the second one, you have a 2 to thickness plus lambda over 2 phase difference, right? This is from the path taken, so the thickness T, and the lambda is for the reflection. So at the point A, thickness is 0, and the first and second waves have just lambda over 2 phase difference. So it means that pi, and they are out of phase. So when they are out of phase, they will have destructive interference. So then this will be dark fringe. So that's why, like, I mean, when the first light comes from this surface, so it has no phase shift, but the one reflecting from the bottom glass has the pi phase difference. So that even though the real phase path difference is 0, you expect they should be in the phase, but because of that reflection, the second one has a pi phase difference, so it's gonna be destructive interference. So there is some explanation. So we have another observation for the thin film interferences. One is called that's called Newton's rings. So when you have a, say, surface of a lens placed on a flat glass here, so you have also some path difference, and as you go further and further, the path difference gonna change. And you will see the rings instead of just fringes. So if you look at from the top, you will see dark, bright, dark, bright, dark, bright rings. And the relation is not gonna be linear because of this slope. It's parabolic. As you go further, it will have a more faster change. So we will see these Newton rings. So actually this is very useful to check the quality of the surfaces. So for example, this is a perfect surface for the lens, but when you have something like this, it means that it's not perfect. It just has a lot of, it's not a perfect spherical surface. So this is very useful. As you see, as you go further and further in the outside, rings are denser because it's not a wedge, it's exactly a flat wedge. So for example, this flat wedge is constant change because of the same angle, but when you have a parabolic surface, this change is parabolic, it's not constant. So that's why the outside rings are denser. At the center, it's not that dense. So the interference in nature occurs a lot. For example, in the butterflies and in different animals, you see that the different colors are given because of this interference patterns from the wings. So by using electron microscopy, we can see that fine structures. So for example, one application for the thin film interference is making anti-reflected coatings, or for example, the non-reflecting film, which will have the quarter of the wavelength. So when the first film, okay, so now you have this condition, glass, film, and air refractive indices. So the first one and the second one, they both reflect from hard surfaces. So both have pi phase difference. Then the only thing we need to take care is the real path difference. So from this you have 2t path difference. So the thing is, you want to minimize the reflected light. So you, for this purpose, the reflected rays, first and second one, should have should be out of phase. So which means that they need to have a lambda over 2 phase difference. So what you do then, if you have this 2t being equal to lambda over 2, t will be lambda over 4. So again, this is the wavelength in the film. So by this you can get a non-reflecting film or anti-reflecting coating. Okay, the polarization concept is very important actually. So the polarization is the direction of electric field oscillation in electromagnetic wave. So for example, we learned that electromagnetic wave has electric and magnetic fields, and the electric field is oscillating this way and the magnetic field is oscillating this way, and the light propagates perpendicular to both electric and magnetic field, and the direction of the electric field has the polarization angle or direction. Actually, the electric field of the electromagnetic wave interacts with the matter most, not the magnetic side, magnetic field. So that's why we take care of the electric direction more seriously. So the polarization, when you have a light from, let's say, sun, because we have a lot of generator, so light is gonna be unpolarized. So which means that all the photons will have a different polarization angle. So, and by using the polarizer, we can let the certain direction pass or transmit and the block or reflect the rest. So it's like having a rope oscillating and then going through this slit. This goes through. But if you have an opposite oscillation perpendicular to the slit, so you will not be able to get the wave out. So this is kind of one analogy. So when the light passes through a polarizer, only the component parallel to polarization axis is transmitted. So for example, if you have, then the polarizers, like the slit, they have certain axes. So let's say you have x and y coordinate, and you have one light coming with an angle theta with the y. So you have two components, E sine theta and E cosine theta. And if you have a polarizer, and its axis is along the y, so what happens is this E sine theta is blocked, but E cosine theta is gonna pass. And this is the electric field, and in terms of intensity is square. So normally, like E naught, I naught is the intensity is proportional with the E naught, let's say, electric field square, and the transmitted intensity is going to be proportional with the square of the transmitted light, E square, transmitted wave, E square cosine theta square. And you can put this I naught is the incoming intensity. So transmitted wave, the intensity is gonna be less, and the amount of the change is gonna be proportional with the cosine square theta. So another thing is, when do you have unpolarized light? When it sees a polarizer first, it will lost half of the intensity. So let's say you have a I naught, and here you have I naught divided by 2, and then in this example, for example, that we put the second polarizer perpendicular to the first one, so the here cosine 90 square is gonna be 0, so there's no light passing through. So this cosine square law is called Malus law. So he discovered this fact. So for example, we have one, this is called the lens, but it's actually the polarizer, I guess. So you have an unpolarized light and first hits the one polarizer, and it has the angle 30 degree with respect to the vertical. So let's say if you have a I naught coming here, you have half of it because it's unpolarized, and the first polarizer, regardless of the direction, it will reduce the half of it. But now the polarization is with the 30 degrees. For the second polarizer, it's a line perpendicular axis. So now you need to use half of the intensity times cosine square 30. So the angle is 30 between the axis of the polarizer and the polarization of the incoming light. So so what you have here, you have sunglasses, polarizing sunglasses. So when you have this arrangement, you don't see any light because the angle between two are gonna be 90 degrees, so you will not be able to see cosine 90. So when the light scatters from the molecules or the surface of the lake, it's polarized, so that's why you can see a lot of reflection. And sometimes, okay, let's do some example. So you have unpolarized light, and you have polarizer vertical, the first one, and the second one makes the 45 degrees, and the third one is horizontal, making 45 degrees with respect to second one. So let's find the total. Let's say you have 1 watt laser or the sunlight. What's gonna be the final power? So in the first one, it's gonna drop a half. After the second one will be cosine square 45, and third one is gonna have another 45 between second and third. This is the incoming for the third one. After the third one, you will have this one, and the total intensity is gonna be 1 over 2. Cosine square 45 is 1 over 2, 1 over 2, and it's gonna be 1 over 8 watt. Okay, that's all for the polarization, and we have the summary of chapter 27. So we learned about the wave properties of the light, Huygens principle, every point being a source as a spherical wave, and we learned about the wavelength at different medium, learned about Young's double slit experiment, in double slit, how you can get constructive interference and destructive interference. The visible spectrum, diffraction grating, and we learn about single slit experiment. This is the minima destructive interference, d sine theta. We learn about the Rayleigh criteria, it's about limit of resolution, and from the polarization Malus law, when a light hits the polarizer, that's the transmitted light is gonna be proportional with the cosine square theta. Theta is the angle between incoming light polarization and the polarizer axis. So that's all for chapter 27. So we will do some discussion problems, and we will start chapter 29 on quantum physics. See you later.